A few little comments here. Usually when we talk about the wavelength of light, we're talking about the wavelength in a vacuum. But oftentimes we want to know the wavelength in a particular medium. Then we'll often write it as lambda sub n. Now we know that the frequency in a medium doesn't change. The light ray comes in, starts the material oscillating, and that oscillation of electrons causes a new wave at the exact same frequency. But then if we know that speed equals wavelength times frequency, then in general, the speed of light equals the wavelength without an n times the frequency. The speed in any other medium equals the wavelength with an n in that medium times the frequency. And then if we divide both sides, we find that the frequencies cancel and c over v is just n. So this equals n. And in other words, lambda over lambda n equals n, or lambda sub n equals lambda over n. So that's our first important result here. Lambda sub n is just lambda over n. One of the very important things we will try to understand throughout the rest of this chapter is phase differences. How does the location in its cycle of one light ray compare to the other? Remember, we're trying to understand wave optics, which ties this in with the interference problems we studied in chapters 16 and 17. So in this case, we have two beams of light. One passes through N2, one passes through N1. They go the same distance, and they have the same frequency. But if N2 is a higher index of refraction, then it will take longer for the beam to travel through it. As a result, it will go through more cycles. Seen another way, the wavelength in N2 will be shorter, and therefore it'll take more wavelengths to get the entire distance. We can illustrate that with our little lines of wavefronts from before. As you can see here, getting to the end is almost exactly 1, 2, 3, 4, 5 of the longer wavelengths, but 5 of the shorter wavelengths does not reach to the end. In fact, it's almost 6 wavelengths before we get to the end in this upper case. So it's a further number of wavelengths, not a further total distance, but a further number of wavelengths. It's important to recognize that a phase shift of 1 wavelength is equivalent to 2 pi radians, or 360 degrees. A phase shift of half a wavelength would therefore be pi radians and 180 degrees. And we know from before that if two waves have one that looks like this and another one that looks just the same but shifted by 180 degrees or half a cycle, then they will nicely cancel out and essentially get nothing.